So anyways, today we're going to be talking about graphs, and then with the amount of time we'll have, we're going to see what a graph is. We're going to learn some properties of what a graph is. You may know this as a network, for example, and how we can represent these kind of graphs, and also learn about how we can explore a graph. And depending on how much time we have after all of this, I'm going to be doing a little bit of trivia, kind of talking about some kind of nuanced things that are commonly maybe said during a lecture or in a course, but is often not shown to you. So, sorry, there was some random thing just floating there. That was some funny thing. It'll look better afterwards. But anyways, let's start talking about what a graph is. So I think that's a good place for us to start. So the first thing I really want you to know is that graphs a fundamental combinatorial object. Of much study in the mathematical sciences. So that's like computer science, statistics, mathematics. You should not look at this topic as only just a computer science thing. This is a topic that spans several other mathematical sciences. So just be aware of that. So that means that things that I talk to you about here will hardly cover everything about graphs. In fact, there's so many things I could talk to you about graphs that I could easily just go on for hours upon hours upon hours. And you could take whole courses just on this subject alone, like even just parts of it. So a first good place I could start is that you could imagine you have a network. So like a computer network. So for example, the thing that you're watching this video on. So the data that you're getting processed to watch this, especially if you're watching this over the internet, is over a computer network. So this is just a very simplistic picture. By no means is this as sophisticated as the World Wide Web or anything like that. But you can imagine you have some clients, some servers. So the clients are connecting to the servers to gain access to, say, services. Or they might be, for example, just trying to load up a web page, or who knows? Maybe these three servers are for like a computer game, and these three servers are managing the deployment of communications between players over that network. So suppose that maybe these two users are connected to this server. Maybe have these two here, and then say these three servers are connected to each other. So this is an example of a computer network. And yes, that monitor over there is again probably a little too hot. It sort of looks like it's melting. So that's an example of a computer network. So you're going to see that these computer monitors, which are just representing what your computer or some client's computer, and these servers, they can all represent just a single entity in a graph. We're going to see this in a moment. And these connections between them, they're going to form what we call edges. So I'll talk more about that in a little bit as well. So another example is a flight map. So I'll show you just an example of what I mean by this. By no means would I recommend this as just like a perfect model of this, but most certainly this is an idea for how you can represent all sorts of different things. So it's an effective modeling tool for things that have relationships between each other like this. So I'm just going to label out some airports. Whoops, let's make this one R. YVR. Bonus points if you know what the acronyms of these airports are. But what you could do is you can imagine you have flights that go between these airports. So say if somebody wants to go from YYC to YWG, they can take a flight from YYC to YWG. But however, YVR, if I want to go from YVR to YUL, I have to go through another airport to get there. And this is represented by hopping from one of these to the next one. You can look at this like a path. So this route from one airport to another to another. This is what I mean by it being a route map. So these are going to represent the relationships between trips that planes can take from one airport to another. And those people on the aircraft, they can travel using such connections. Hence the literal term connection. So when you hear about like, oh, we have a connecting flight, I'm talking about these. So if you want to go from here over to there, this is an example of a connecting flight. So what I could do is I can even place weights or distances on the edges, these edges that connect them. They can represent, say, the cost of fuel to go from this place to another place. It may, for example, also may represent a physical distance from this to here. So you can use these edges to represent all sorts of different things. So just for the sake of completeness, I'll fill in the rest of this picture so we have an idea. By no means am I saying these are accurate, but they most certainly will be somewhat accurate. One other thing I should also point out is in a graph, more generally, you're going to see that these connections, the way they're organized, doesn't actually have to make any logical sense other than that they're connected to each other. So it's the connections between what we're going to call vertices or nodes, these circles here, or in our example, airports. These are the relationships between these in terms of their connectedness, so how connected they are, or if they are connected, or what matter when we talk about a graph more generally. There's more specific cases when you're studying graphs where the actual drawing of the graph might actually matter. But for general graphs, that is not actually the case. So it wouldn't have mattered if I put y, y, z up here. It wouldn't matter if I put YWG over here. It doesn't make any difference. The connections between them that matter. So you're going to see that very often when I draw these. Even if I were to assign, say, distances or anything like that to these edges, it doesn't make any difference. Hopefully that is clear. 2303. Let's go 3,222. Yeah, that sounds about right. And we'll say 4,184. I think I got all the edges. I think I got them all. So this is an example of flight routes with distances. So you can see if ever I wanted to say find the shortest route from say YVR to YHZ, you can look at these distances and try to figure out what pathway or which sequence of connecting flights gets me from YVR to YHZ. So you can see, for example, there's at least one way to get there. So you can say go from YVR to YYC to YUL to YHZ. But keep in mind that may not necessarily be the shortest one. So I'll let you think about that. So that's something that maybe in the future I'll talk more about, is computing, say, the shortest pathway from one airport to the other. So these are two example applications to help you give you a flavor for this. But like I said, it's the connections between these entities. So in this case, these were airports, or in this case, they're computers. It's the connections between these computers that really matters in a graph. So while you see servers and clients, which sure you can represent more information with these if you knew, like this is like a type 1 computer, type 2, or whatever it might be. Fundamentally, when we talk about a graph, you can have that extra information, but ultimately for studying the graph itself, which I'm going to define shortly, what matters when you look at this graph here, because this is really just a graph, it looks something instead like this. So you have, really, I'm just going to reduce it down to the connections between them. right? So those are all the connections between the computers, right? So each one of these I can label. So I could call this one V1. I'll call that V2. This may be V3. Let's say that's V5, V6, that V4, V5, V6, V7, V8, V9. These may have different labels on them. That's an example of a labeled graph. So these labels may correspond to indices. So how you represent the graph may help you kind of label what they might be like this. But right now we're working at the level of this concept of a graph. It's these interconnections between entities. So we're going to call these entities nodes or vertices, singular vertex. And these connections, these are going to be dictated by what we call edges or an edge. And depending on what the relationship the edge has, we have somewhat different terminology for it. So we're going to talk a little bit about some terminology in relation to this. So hopefully that's pretty exciting. I'm pretty excited. Hopefully you guys are excited. So let's head on over here and let's define what a graph is. So I must stress that there are several ways you can write the same definition down. But let's talk about what a graph is. So at first it's going to sound a little abstract if you've never seen this definition before, but I'm hoping that I'll be able to encourage you to see really that you already know what this is. It's just that I have to write it out a little bit more formally for you. So it's going to be a pair, capital V, capital E, where capital V, or I'll just call it V, is a set of vertices. So those entities that we've been talking about, like the things like, say, those airports over there or the computers over there, these are examples of vertices. So the servers, clients, those are just computers. Same idea. Those airports, they're all just entities in the relationships that I have here, and these are what we call vertices. Sometimes they're called nodes. I must stress, this is a common mistake students make, is they say, when I tell them the singular of what vertices are as just a single one, it's often a common mistake to pluralize the singular. So let me explain. So the singular of a vertices is vertex. So you may have heard of this word from geometry, for example. So it is not, the plural for vertex is not vertexes, it's vertices. It's one of these fun words. So please, just for the sake of me, just please don't say vertexes. It just gets so weird. So sometimes it's a set of vertices or nodes. And capital E, which I'll just call E, is a collection. It's a collection of pairs of vertices, which more broadly I'll just write like this, with rounded parentheses, UV like this. But I must stress that you can impose extra meaning onto what an edge is, which I'm going to talk more about in a moment. Called edges. Sometimes these are also called links. It often depends on kind of the context you're talking about it. Or arcs. So for example, when the edges form just a singular direction in the relationship. So one entity is only related to another one, but not the other way around. Sometimes the word arc is used selectively in that regard. So one other thing is take a convention for our discussions here, just also abbreviate some discussion here. So just some convention I'm going to be using is that the number of vertices in a graph, that looks like suspiciously like an E. I'm going to fix that. A number of vertices is, which we can denote with the cardinality sign, which this means the number of elements in this set. We're going to write that as n. So n is going to be the number of vertices, and the number of edges in the graph, which you can denote with the cardinality or the size of E, which is just the number of pairs there are, with M. So it's just the convention we're going to follow. So I thought we'd do one. So just to really illustrate this point, just to re-emphasize it, because I think it's really important for us, is say, for example, in our application over here with the route map here, our flight routes. So the set of vertices here would be your airports. So each one of those, there'll be a one vertex. And say, for example, like we have a connection between YUL and YHZ. This would, for example, say YUL, YHZ would be an edge in this graph. So, for example, YUL, YHZ, that's an edge in this graph. So we'll call this, for example, an undirected edge, because you can go from one way or the other way. Now, maybe there's a much more robust model, for example, that may have multiple relationships encoded that only have one direction or another, which sometimes happens with some airports, by the way. Sometimes they have it where a route only goes from one airport to another, but not the other way around. For example, you can think of international flights. Sometimes there's only, like, they only return from a place, but they may not go to that place. You may have to go through a couple other places to get back there. Say, for example, if it's about reducing costs. Let's draw a picture. I think it's important that you see pictures. Pictures, pictures, pictures. I'm just going to draw with this graph. I think it's a pretty cute looking one. The one thing I will tell you up front is that graphs can be really pretty to look at. And I'm going to try, with how much time I have here today, to kind of expose you to just maybe some different kinds of graphs. But I could easily go on and study all sorts of different kinds of graphs based on the relationships they have with each other. So here's an example of a graph. I've labeled the vertices with these alphabetical letters, but that isn't necessary at all. These could be numbers. In fact, technically a graph doesn't even have to have labels on it for the vertices. But this is important that we have some way of knowing which vertex is which vertex. So you can think of these as the names of the vertices. Otherwise, I would usually call them like V1, V2, V3, V4, because the labels don't really matter a whole lot. So here's just an example. So in this case, if this is graph G, then if I say graph G is equal to VE, this would be where capital V is just going to be the set A, B, C, D, E, F. If you're not familiar with these squiggly curly braces, they just simply, this is notation to say, hey, look, all of these are a part of this set. The order I write these out doesn't matter, just to be very clear. So it could have been just like F. I could have wrote these all backwards if I wanted to. It doesn't matter. As long as they're present inside of the set. E, well, this one, it's going to be a collection of, now, one thing I want to point out is that I brought this up, is that you can have different kinds of edges. So you can have what we call directed edges, you can have undirected edges, you can have things called mixed edges. There's all sorts of different kinds of edges that can exist for a graph. So in this case, I'm going to write them out in the way I will shortly for an undirected graph. So you'll notice that, so when I talk with directedness or a directed graph versus undirected, what I literally mean is I'm gonna like draw arrows on these, meaning that you can kind of only go in one direction. So if I want to go from A to B, if I put an arrow on here, this means I can go from A to B, but I can't go backwards. So let me write out these in the sense that I will very shortly for an undirected edge. So notice there's no arrows or anything I've drawn on these. There's no sense of direction on the edges, hence its name. So I can have A, B. So note that if you really don't like this syntax or notation, you're welcome to, for example, just use rounded parentheses like I wrote over there. You can write that just right here, and it doesn't make any difference. Just the point is that the order in which I write them does not matter if it's what we call an undirected graph, which I'm going to define shortly. So AB, AC, AF, AE, BD, CD. Man, I could go for some music. And we got DF. So here's the graph. So notice that in our case here, notice that I have AB because there's this edge right here. I have AC. Notice that edge is right here. AF, right there. AE, right there. BD, where's BD? Ah, there it is. It's right there. It's right there. BD, we got CD right there, and we got DF. That's all the edges, right? So this is how I could write out a description of this graph. So sometimes it's helpful to draw a picture to show somebody what the graph looks like. It may be helpful to describe it in this form. This is the formal way you would write it. This is the informal drawing. So sometimes drawings are going to be very helpful to understand what's going on with a graph. So let's talk about this whole edge business now. So let's talk about what because I talked about this idea of a directed edge, undirected edge. Like, what does that mean? So let's kind of talk about that now. So you're going to see that I'm sort of going to unpeel a lot of what we just talked about here. I also brought up this idea of connectedness. So like, what does that mean? So we're going to talk about that too. So suppose we're given an edge, E, which is going to be, suppose it has these two vertices as its pair. Suppose it has those as its pair. What I would say is that U and V are endpoints. Are endpoints or end vertices, which it's not as common as the first of these two, but I've seen it used before. End vertices is two words of E. So these would be referred to as the endpoints of E. So if ever you want to talk about like, okay, here's this edge, what are U and V? They're the endpoints. So you can think of it like almost like if I picked up one of these edges over here and I just like picked it up like this, like a dumbbell. I'm just trying to like lift it. I want to know what vertices are on the two sides. They're the endpoints. So I must stress that there's different edge types. So let's talk about edge types. You're going to find that the former is far more common than the latter, at least when we talk about graph theory. So keep in mind that keep in mind that when people describe graphs to you, they're very often going to talk about just a concept of a graph. Usually when they say stuff like this, they're going to presume the first of these two, almost always, with the exception if they actually just straight up tell you. So just to be clear. So these are just examples of edge types. So you can have an undirected edge. So this is an unordered pair of vertices, U and V. So I must stress that when I wrote out those pairs over there, the reason why I use the curly brackets there is, like I said earlier, it doesn't matter what order you write them in curly brackets like that, or curly braces. This is just a syntax. This is just a way to denote this, is that it's unordered. Sometimes that actually really matters. So this is denoted either as UV with the rounded parentheses. Usually my advice when you use the rounded parentheses is make sure it's clear that you're talking about an undirected graph. So if you define what your graph is, usually a helpful tip I can give you if you plan to use this notation is make sure when you define the graph, say it's an undirected graph. And then this will avoid any confusion about what that is. Or you just simply say it's an undirected edge, and then you just give its name like this. So some people will write this as UV with curly braces. Sometimes even people will just literally write UV right beside each other, just one after the other like this. I find this is far more common in graph theory circles. But I must stress that it doesn't make any difference. UV, it's supposed to be a V. UV is the same as VU. There's no difference between those two. They're the exact same edge. So the fact it's undirected means that it doesn't matter what order you tell me the endpoints of the edge. It doesn't make any difference. This is in contrast to a directed edge. So this is actually an ordered, so this is actually where the order matters with the endpoints. An ordered pair of vertices, UV, where the first vertex, so the first of these two listed, so like example U here, the first vertex U, first vertex U is the origin. Some people call it the origin or the tail of the directed edge. And the second vertex, is the destination. So some people call this also the head of the edge. Caution to the wind, if you use the term destination, if you talk about like some routing problem, like our flight map application that we talked about, I would probably not use that terminology because it sounds like you're going to that place. Now, in the context of an edge, as you're going to see my picture just shortly, it's going to be where, like straight up, where if you go from one to the other, if you follow the arrow tells you where you're going, which makes sense why you'd have an origin versus destination in that sense, which could be contrasted with an actual route where you have a pathway from one place to another, which has its origin and destination, which in that case, if it's a directed graph, would be a sequence of origins and destinations, one hop to another to each vertex. So that's just a little bit of caution from a communication standpoint. And is sometimes called an arc. So sometimes, that M is looking a little suspect there, and is sometimes called an arc or directed edge. So in fact, it would be called directed edge, right? Sorry, I'm getting very excited here. What I'm saying is that some people call this an arc to contrast it with an edge, which sometimes they talk about as just an undirected edge. So the default is an undirected edge. These are more specializations on top that can generalize over this concept. So let me draw you a actually one other remark I want to make. So please don't mind. I know this is a lot of terminology, but you'll thank me later. If E is equal to UV, then E is directed from U to V. So that's a very common phrase you'll see. And this is very often abbreviated as U with an arrow V like this. So if you want to give me a sequence of following directed edges, so if you have a whole bunch of them like on our flight wrap, where you want to go from one airport to another, you can almost look at this like a chain of these, if say you have directed edges. This is also one way you can also describe to somebody a pathway, but in directed edges, it's much more helpful as an abbreviation like this. So let me draw you a picture just to encapsulate both of these points, because I think it's important that you gotta get this all clear. So an undirected edge, So if we want to talk about an undirected edge, so if you have UV, this is very often how it will get drawn. You just have a line like this between the two. Keep in mind, it doesn't have to be a straight line, just to be very clear. It could be curved. It could be, it doesn't have to be a straight line, just to be very clear. It's just a connection between the two like this. And this is what UV is. So this is what an undirected edge, or edge, which I'll very commonly just call this an edge, just by default, would look like. This is in contrast to a directed edge or arc, where if I give you, there's actually, the order does really matter. So if I give you two cases, suppose I have U and V as the endpoints of the edge. The question is, if I were to draw these two different directed edges, how would I write them? Does anybody have any ideas of how I can write this out? Any ideas at all? So if these are two arcs, just to be clear. So I have, so if you look at this, if you look kind of like at my abbreviation here, it really gives you everything you need to know. So if I give you an edge UV, like this, notice that this is actually this edge right here. So this right here, in our example, I'm just going to kind of draw a box around this to help distinguish it from what's above. This is the directed edge UV. However, this right here, the bottom one, is actually the directed edge VU. Notice that it goes from V to U, versus this one goes from U to V. So this is an example of an arc, or directed edge. Very interesting, right? Now that we've defined some edge types, now I can define different kinds of graphs for you. So let's talk about this. So once you get a grasp over this terminology, it becomes much, much easier to navigate any discussion about graphs. So kind of the goal of the first part of our lesson here is really kind of to build on some of this terminology so we have an idea of what a graph is, what are some common terminology so you know what people are talking about things, what they mean. Because it's so easy to just talk about lines and dots and talk about things being connected or not. But it would be nice to have a consistent language that we can talk about these things. Now, I must stress that not every graph theorist talks about these terms in the exact way. So if ever it's unclear, you just ask them to give the definition to you, okay? So there's different graph types too. So now that we have definitions for edges, for example, now I can define, for example, different kinds of graph types. I must stress that these, again, aren't all possible kinds of graphs that you can define. These are just some common examples. So I mentioned about the concept of an undirected graph, which very often when people talk to you about graphs, they usually presume it's an undirected graph. Just in the same way when I talk about an undirected edge, people will just call that an edge. So again, just carefully read the context. So an undirected graph simply is a graph where all the edges are undirected. Piece of cake, right? There's nothing too sophisticated about the terminology. It's like, sure, I could say it's not sophisticated, but it's very effective, right? You don't have to, like, if you read this, you're like, okay, that's the definition, right? Like, it seems pretty darn straightforward, right? So naturally, you can have the concept of a directed graph too, which I will tell you that often people will abbreviate this as a digraph. Very often when you talk about directed versions of graphs, they usually like to put this di in front. Not like die, like no stabby stabby. I'm talking di. They'll put die in front of it. So if like some people even refer to a directed edge as a die edge. So this is just simply a graph where all edges are directed. Pretty straightforward, right? At least I hope. Naturally, you can also have a mixed graph. A mixed graph is a graph where edges may be either undirected or directed. So in this kind of representation, the way it would work is that some of the edges will be where you can kind of go back and forth like this, but its meaning is that it's treated like a singular edge, just one edge. This is in contrast to the directed edge, which would force you to have it where, if say like our example with the flight route map, you would have it where you can only go from one airport to another, but you can't go the way around. You'd probably have to find another route. But the point is, in that representation, the way it would work is that you can have, so some routes can only go from one airport to another, but there may be flights that can go back and forth over just a single edge. Now, one thing I do want to mention to you, this is always something that's important to talk about when we start talking about graphs, is I showed you a bunch of different types. Now, there's actually relationships different graph types have with each other, but you also need to remember that a graph isn't just simply just like usually when people use graphs, often the important thing is they're trying to model something. So there's some meaning that gets imposed on what the graph is. So give it some formal definition, and it's supposed to represent something. So sometimes the way the edges are defined and sometimes the way the graph is represented can actually make or break actually what you're representing. So let me give you an example of how you can represent any undirected graph as a directed graph. So if I give you a graph that looks like this, very simple graph. This is something that we would call a triangle. See, because it looks like a triangle. It doesn't have to look, it's just three vertices that are all connected to each other. Which I'll have terminology about what I mean by that. So, and when I say that, I'm really saying that if I look at any one of these vertices, notice that they're right beside each other. They're adjacent to each other. Now, I could take this graph and I could actually represent this undirected graph as a directed graph, as follows. So what I could do is I can introduce multiple edges like this. So I could take directed edges and I could put them so they go back and forth like this. But here's the catch now. Suppose that you wanted to represent, say, a route that went from this vertex back to itself. Notice that if you wanted to talk about this concept with that graph, it gets lost in the meaning here. You would need a stronger notion of a route or a pathway. So for example, notice that if I try to go here to there, notice that down there's a directed, so if I follow this arrow, which is how finding or navigating through a directed graph would work, is you can follow the arrow to here. But notice now, you don't have to go to that one. You can come right back up here like this. So, but the thing is, it's literally two edges. So if I'm trying to find a way to go from this vertex back to itself, notice that I can go to this vertex and I can go back to myself. Do you see how the meaning gets lost when I translate over like this? So I would need a stronger notion here if I wanted to model the graph like that over there on the right, as opposed to what I have on the left. So this is actually why I'm talking about different graph types, is that sometimes it makes sense to model your problem that you're looking at, or if you're studying a problem on a graph, to understand that sometimes you can lose meaning for what you're actually trying to solve or accomplish by just merely just representing it slightly differently. So in this case, say a pathway, or in this case, what we'll call a cycle, can actually change its meaning from this graph to that graph over there. But it's still a cycle. It's just that we lose the intuition behind what the original graph was doing. A cycle in this case should be, it should be able to go around and come back, right? This is a case of a cycle where none of the vertices are going to repeat each other. So notice that I could still get a cycle over there. because I'm still not, I'm still got an extra edge I can talk about this notion of connectedness between edges and vertices. So there's two different notions of this that we're going to be focusing in on. So the first one is the notion of adjacency. So you may say this as the following phrase. So I'm trying to give you a formal way of talking about this so it's not confusing. So there is an edge connecting, and I'm going to use quotation marks around this because we're going to use we're going to have this idea of connected for a graph at some point soon. There is an edge connecting two vertices or nodes. So if I give you an edge whose endpoints are u and v, uv like this, doesn't matter what kind it is, I'm going to break it into two cases for you, is in a graph, then v is adjacent to, that E is looking a little bit sad here, adjacent to U. So vertex U is adjacent to U. So I'm going to give you two possibilities for depending on what kind of graph we're talking about, the kind of edge it is, specifically. So in digraphs or directed graphs, V is adjacent to U if you can go from U to V. So meaning you could get to V through U. That's what I'm saying. So I must stress that adjacency in this relationship with directed graphs is not what we call symmetric. It means just saying that V is adjacent to U doesn't mean that U is adjacent to V. Just like we talked about with our picture earlier with edge types, is that you can have an edge that goes from U to V, but you can also have an edge that goes from V to U. They have two different meanings. They're two different edges. So you can have the idea of a directed edge, or you can have one that's like this one we had before where just like it didn't matter which direction you're in. For a directed graph, it really matters. So I must stress that this relationship only goes one direction. So I'll say, note it is not symmetric. So that's a lovely little detail. Maybe we'll put that in the side of our hat or something as a little note, a little pencil, put it behind the ear. So unless you had an edge that was VU, so right now we only have one that's UV, you couldn't say that U is adjacent to V in a directed graph. However, the good news for you is that it's a lot simpler when it comes to an undirected graph. In undirected graphs, I'll say in undirected graph G, an edge UV. So I'll use the curly braces just to indicate that, oh yeah, it's an undirected edge. But like I said, it doesn't matter if it's curly or rounded like that, just as long as it's clear that you're talking about an undirected graph or an undirected edge. So if this edge is in G, it implies U is adjacent to V. and V is adjacent to U. So if we give you an undirected graph, the notion of adjacency, it doesn't matter what order you tell me the vertices. So just as a quick example of what I mean by this, if we had this graph here. So if I give you this graph, you can say that A is adjacent to B, A is adjacent to C, A is adjacent to D, A is adjacent to E. Notice that there's an edge whose endpoints contain A and some other endpoint. The other endpoint is what it's adjacent to. So you can just look at its neighborhood. So all of our friends here that are connected to A. So we would say that A is adjacent to each one of these. However, A is not adjacent to F. Notice that F, there is no edge where you can see that F is in the same pair as A. Hopefully that's clear. In contrast, if this was a directed graph, something like this, what I could say, if this is the case, so I have A as the first endpoint, and then say, for example, B is the second endpoint. And then I could say, for example, that B is adjacent to A. So notice that I can go from A to B, but I can't go from B to A. So hopefully that is clear. So that's the notion of adjacency. It's pretty, I think it's pretty cute. So I'll have another example in my notes. So that's the first notion of talking about edges and vertices and them being connected. So the second one is what we call incidence. So these are two common ways we can talk about edges and vertices in graphs. So I'll give you another thing to talk about. So let's talk about incidence. So incidence. So you know how in the adjacency we talked about vertices, right? We talked about vertices, those that are our neighbors. You can think of them as our neighbors that we can be, they're connected by some edge to us. Well, incidence is actually, it has a dual purpose. The first one is that it allows me to talk about edges that are shared by a common endpoint, but also if I want to talk about a singular edge and I want to know what one of its endpoints is. So it kind of has two purposes like that. So you're going to see that carefully here. So two edges, E and E prime, are incident. So we would say E and E prime are incident if at least one endpoint, remember those are the things that are sticking on the ends of these edges, those vertices are nodes, at least one endpoint of E and E prime is the same. So very commonly the phrase would be used as follows. E is incident with E prime. You can also say E prime is incident with E if we're dealing with undirected edges. So that's one notion you can use this idea. So another thing I should point out is that you can talk about the relationship one of the endpoints has with an edge using this concept as well. So furthermore, in an undirected graph, in an undirected graph, edge uv, so if I have two endpoints u and v for an edge, is said to be incident on sorry, I'm getting really excited here. Incident on vertices u and v. So now you have, if you give me some edge E, what you could do is you could talk about the edge being incident on one of its endpoints. So that's very common if you want to talk about an edge and you want to say, hey, look, this edge has this other endpoint. And that's the thing about a reference I want to talk about. This is how you can do it. So I must stress that you can have the notion of incident from and to in a directed graph. So I'll make a remark about this. So in digraphs, an edge uv, so remember it's an ordered edge, so it's directed. So remember it's a digraph, it means it's a directed edge, so this is technically an arc. So just be very clear. I'm trying to expose you to several ways somebody can write this stuff down. So remember this is an arc. So is incident from or leaves. Sometimes people use the phrase leaves vertex u, and is incident to or enters. Sometimes people will talk about entering a vertex. Enters vertex v. And that's everything really much about incidence. It's not terribly interesting as a concept. It's useful for language, just like the concept of adjacency. And you can use these two different notions to represent graphs. So I guess for the sake of purpose, I should really just do another example just to kind of illustrate it. I'll use the same graph I had over there. So I'll draw out another graph here. There's nothing special, by the way, about this graph. I'm just sort of just drawing it out. So I have A, B, C, D, E, F. So suppose I pick this edge right here. So first, just be clear, this is an undirected graph, right? Because it has no directed edges in it. So notice that I have an edge. Suppose I look at this edge. Well, I could say that if I call this E, which is kind of confusing because that's a vertex, I'll call it something else. Let's call it Z. So edge Z is incident on vertex A. It's also incident on vertex B. And also, if I had another edge that shares a common endpoint, say this is edge Y, I can say that Z is incident with Y, because these are two edges, they're shared by a common endpoint. But I could not say that Z is incident with this edge over here because it's not sharing a common endpoint. They don't share a common endpoint. But I'll let you think about how you would adapt this version for the directed graph. I'm going to define the idea of a parallel or multi-edge or multiple edge or multiple edges. So these are additional things you can do to a graph to further generalize it. multi-edges. So, you know when I drew the picture at one point and I showed you, hey, look, you can have like edges. You can have multiple edges that go between two endpoints. You could say that both of these edges are incident on A and B. In addition, you can also even have it where an edge has both of its endpoints being the same vertex. So this example here where I have two edges, two what we call parallel edges, or two multi-edges, or these two edges here, and I also have a self loop over there, or some people call that just a loop. So parallel or multiple edges or multi-edges, these are two or more edges, with the same endpoints. So it's the endpoints that matter here. Likewise, we can also have the idea of a self loop or just loop. Some people call that a loop. One thing to be watched out for is that some people will call also what we call define later as a cycle. They also call that a loop too. So just be careful. So that's why usually I refer to it as a self loop. So it's an edge whose endpoints are the same vertex. So these two edges are examples of parallel edges. This is a self loop. Naturally, once you have these in place, now you can define some more types of graphs. You can define what was called a multigraph, which is a generalization of a graph. So this is a graph with multi-edges. So it has multi-edges, and typically it has self-loops as well, but it doesn't have to. You have to, like I said, you have to carefully look at how the author is formulating this for you. But usually, this is my experience in research, it's very often a multigraph will have multi-edges and self-loops. And another thing to keep in mind is the idea of a simple graph. So this is going to be a very common one. So this is a graph with no multi-edges or self-loops. So for example, that graph up there is not a simple graph. However, for example, like the triangle, that's a simple graph. All the examples we drew on the board up to this point, they're all simple. So all the undirected graphs I gave you, they're all simple. So I must stress that going forward, if ever I talk about a graph, so please keep this in mind, is if going forward, I want you to assume that the graph is simple. And if I don't say anything else, just also assume that it's undirected. So please keep this in mind. I must also stress that many of the concepts we're going to be talking about generalize over several different kinds of graphs. So just because I'm talking about it as an undirected graph doesn't mean that you can't do it to a directed graph. So just also be keeping that in mind carefully.